In lesson 1.17, you'll learn to use direct variations to solve real-world models as well as inverse variations. Let's begin with what a direct variation is. A direct variation is simply the relationship between two variables where the ratio is going to be constant. Y over X is going to be constant. Graphically, what this simply looks like is a line that goes through the origin, like the ones you indicated right here in this diagram. So no horizontal and vertical translation. And y is equal to kx means that y is directly proportional to x. And because this is going to be constant, this proportionality for k, this is called the proportionality of constant, or the constant proportionality, is equal to the ratio of y divided by x. And as I stated earlier, we use the equation y is equal to x when we say that y varies directly as x, or that y is directly proportional to x. These two statements implies that we have the equation y equals k, a constant, times x, the constant proportionality times x. So let's look at some examples of direct variation. Now, here we state that the state tax is directly proportional to the gross income in Pennsylvania. So the tax is directly proportional to the gross income means that y is equal to k times x. But instead of using the generic values of y and x, let's use t for tax. Let me do it in black instead. T for tax is directly proportional. We'll multiply our constant with the gross income, which we'll use G for the gross income. So here, this is the relationship between the tax and the gross income. T is equal to K times G. Now, using that relationship, if you make a monthly gross income of $1,500, so if your G is $1,500, then your tax T will be $46.05. And the first thing that we need to do in these type of models, in these direct variations and also inverse variations, is to first figure out what this constant of to. So in this situation, our constant will equal to 4605 divided by the 1500, because we're looking for what number times the 1500 is equal to this total. So we do this by using inverse operations and dividing both sides by 1500. And we end up with this. Let's divide $46.05 by 1,500, and that's going to equal to $0.0307. So now with our constant, we're going to replace this constant into this value of k, and t equals 0.0307 times g. So now I can figure out the tax at a different gross income if somebody makes a different amount of money a month, or figure out how much you need to make to only be taxed a specific amount, like $50 or something like that. But in this question, we're asking to figure out the state income, so we're looking for T when the income is $2,500. So what is T going to equal to when the amount of money, the gross income, is $2,500? So let's replace now G with $2,500. Then that's going to give us a total of $76 with 75 cents. That's going to be the taxes on $2,500. And there's your answer. Let's look at another example. So like on this example, if I go to the very end, just look at the question, how many square feet is a room that takes 10 hours to paint? So we want to figure out how big a room is going to be if it takes 10 hours to paint. And well, first we have to look at the relationship between the size of the room and the time it takes to paint it. And according to the very first sentence, it says that the time it takes to paint a room is directly proportional to the area. So that means that y, again, since it's directly proportional, y is equal to k times x. But for y, let's use the letter t for time, k times x, and for x, let's use a for area. So that way it's more relatable to this scenario here. So if it takes 4 hours to paint a 200 square foot room, so 4 hours is the time, and the area is 200 square feet, that means we're going to get the constant of proportionality by dividing 4 by 200, which in fraction notation is 1 over 20. But let's write this as a decimal, which is 0.02. So now we can figure out the time it takes to paint a different size room by simply multiplying this constant, which is 0.02, with the area. Or we can figure out the size of the room. Like in this case, we want to figure out the size of the room when the time is 10. So let's substitute in 10 for t and solve this equation. Well, right here, because we're multiplying, we're looking for the value of a, and it's being multiplied by 0.02. We're going to divide both sides by 0.02. So a would equal to 10 divided by 0.02. And that's a total of 500. Sorry, this number right here should be 50. 4 over 200 reduced is 1 over 50, not 1 over 20, 1 over 50. And there's your answer. So it takes, the size of the room would be 500 square feet in order for it to be painted in 10 hours. Now, moving along, we can multiply again our constant with various things with more than just one value right here. Like here, this next one, there's a multiple relationships. We want to figure out the distance a ball travels after 6 seconds. So we want to know the relationship between the distance and the time that a ball is going down an incline. According to the first sentence, we have that the distance that a ball is going to roll an incline is directly proportional to the square of the time. Square means that we're raising something to the second power. So when we square something, that means something to the second power. So in this case, it would be x to the second power. So our distance, our y, equals to k times x to the second power. And instead of using y, we're going to use d for distance. Directly proportional multiplies our constant with our x, which in this case, we're going to use the letter t because it's for time. But it's being raised to the second power because, again, we're squaring it. So after 3 seconds, the ball rolls 72 feet. So replacing d with 72 feet, that's the distance. Replacing our time with 3 and squaring it, we end up that 3 to the second power is 9. So this is 9k. So the way we're going to figure out the value of k is by dividing both sides by 9, specifically dividing 72 by 9, which equals to 8. So the relationship between the distance and the time is that the distance equals to 8 times our seconds raised to the second power. And if I want to figure out how far a ball is going to roll after 6 seconds, I'm going to replace the time with 6, square it, and multiply that with 8. So this is 8 times 36, and 8 times 36 equals 288. So that's the distance that the ball will roll down an incline, or the distance traveled when a ball rolls an incline plane for 6 seconds. Let's do another example of this where our proportionality is multiplied with various things. And on this one, it didn't look like it was multiplied with various things, but it is, because t to the second power technically means t times t. So k is multiplied with two things, not just one. It's multiplied with t and then with another t. Now let's see when we multiply two different things with k. Not the same thing, but two different things. Like in example number 4. The energy absorbed by material is directly proportional to the product, which means to multiply. Product multiplies its density and the square of the velocity. So here, the energy absorbed is directly proportional to the product of the density and the square of the velocity. So y is equal to k times x and some other units w, all right? So y we'll use, the energy absorbed, let's use the letter E for energy. That is directly proportional, so k is multiplied with the density, we'll use d, and velocity, and v. And the reason we're multiplying it, because that's what it says here. It says the product. So we're going to multiply v and d. But the v again is squared, so v is raised to the second power. Now, a material can absorb, so for example, a material can absorb 400 joules of energy. So the energy is 400. We don't know our constant. When it's hit by a projectile at 10 meters per second and has a density of 2 kilograms. So our density is 2, and our velocity is the 10 meters per second. So 10 to the second power. So again, remember, these are not decimal points. These are time symbols. So k times 2 times 10 squared. So let's start by first simplifying this and figuring out what this is. Well, 10 to the second power is 100, and that multiplied by 2, that's 200. So k is going to equal to 400 divided by 200, which is simply 2. So the relationship between the energy, the density, and the velocity is that the energy absorbed equals 2 times whatever the density is times the velocity to the second power. So now here we want to figure out what the energy is going to be when the projectile is hit by 15 meters per second and it weighs 3 grams. 3 kilograms per, with density of 3 kilograms per meter squared. So our density is 3 and our velocity is 15. So 2 times 3, that's 6, and 15 to the second power, that's equal to 125. So 6 times 225 is equal to 1,350. I'm sorry, 225, not 125. 15 squared is 225. My mistake. So here is our answer. Now let's move on to inverse variations. Inverse variations does the opposite operation. Instead of multiplying our constant with x, it divides the constant by x. And we know that we use this formula here by the following two statements. If we say that y varies inversely as x, we divide k by x. If we say that y is inversely proportional to x, that means again that k is divided by x. And since k is divided by x, the way we get our constant this time is by multiplying our x and y values together, by multiplying these two quantities together. So to solve real world models using inverse variation, we have to again first figure out what the value of k is, plug that in, and then using that formula with the k, we can again evaluate and solve a real world model situation like the one right here. Here, I want to figure out demand when the price of a product is $5. So I first have to look at what the relationship between the demand of the product and the price is. So a company found that the demand of one of its products varies inversely to the price of that same product. So what this implies means is that y is equal to k divided by x. But instead of using the generic variables for y and x, let's use d for the demand. Varies inversely, divides the k by the x value, and let's use p because it varies inversely to the price. That's going to be the x we're going to use. So instead of using x, we're going to use p for price. Now let's plug in from the second sentence. We have that the price, when the price is $6.25, the demand is 400. So the demand is 400 when the price is $6.25. So here, to figure out the value of k, we're going to cross multiply and that's going to give us a total of 2,500. So k equals 2,500. So now with that number k, we can now have a formula for the demand. So the relationship between the demand and the price is that the demand is going to equal to $2,500 divided by the price. So here we're going to change the price from 6 to 5. So let's substitute in $5. And our total is going to be 500. So the demand is equal to $500. So decreasing the price by 75 cents increases the demand by 100. And then there's a lot of different things we can do from this. We can then looking at how much it costs to produce this item. We can determine again if it's cost efficient to sell them at $6.25 or keep them at $5, depending again, because we're going to make the same amount of money regardless, but is it going to be more cost efficient because of the shipping and all the other stuff that goes into this? So there's a lot of other variables again that we can move, and we can make this problem a little bit more interesting again from this point on. But in this situation, again, we're just simply scaffolding and building on how to create, again, the initial situation and determine, in this situation, the demand for an item that's going to cost $500 if it initially was $400 units was in demand for at a price of $6.25. Well, let's move on, and let's now look at another example again. Now, in this next example, we can now also combine variations. We can now combine variation. Well, I'm sorry, not combine. This is another example of an inverse variation. So, sorry, this is wrong. This is another example of an inverse variation. So let's say that the focal length of a lens is inversely proportional to the object's distance. So the focal length is inversely proportional to the object's distance. So what does that mean? That y is equal to k divided by x. So for here, let's use L for the y, k divided by x, and let's use d for distance for our x. If a lens has a focal length of 20 centimeters, so if L is 20, when the distance is 10, we can calculate k by multiplying 20 and 10, which is 200. So with k, we now know specifically that the relationship between the focal length and the distance of the object is that the length will equal to 200 divided by the distance of the object. So what is the focal length when an object is 50 centimeters away? That's going to equal to 4. Yeah, 200 divided by 50 is equal to 4. So the length would have to be 4 centimeters. Now, Let's look at an example of a variation where we can combine a direct and an inverse variation. A gas law states that the volume of an enclosed gas varies directly as the temperature and inversely as the pressure. So the volume of a gas varies directly to the temperature and inversely to the pressure. So what this means is that V, volume, is going to equal to K, and the K is multiplied with the temperature because it varies inversely, but then it's going to be divided by the pressure because it varies directly, so we multiply with the T, and it's going to vary inversely, so we're going to divide this K by the P, by the pressure. So we use P for pressure. So this is the relationship between the volume, the temperature, and the pressure. So we'll have to start by first again figuring out the value of K. Well, we're given here in the second sentence that the pressure of the gas is 0.75 kilograms per by square centimeter. The temperature is 300 kelvins, and that's going to yield a volume of 8,000 cubic centimeters. So in order to figure out K, we first want to simplify this. So here we're going to divide the 300 by 0.75. And that's going to equal to a total of 400. So we have 400 K. And we're going to get the value of K by dividing both sides by 400. So 8,000 is divided by 400, which equals 220. So substituting in K, we get that the volume is equal to 20 multiplied with the temperature and divided by the pressure of the gas. So now let's find out what that volume is when the temperature is changed to 750 and the pressure is changed to 1.875. Here I recommend that you multiply this together first. So 20 times 750, that's equal to 15,000. And then divide that answer by 1.875, which is going to, coincidentally enough, is also equal to 8,000. So that's the volume with that temperature and this much pressure. Let's look at another example. The resistance of a wire varies directly to its length and varies inversely to its area. So the resistance of a wire varies directly to its length and varies inversely to its area. So what does that mean? That y is equal to k times x and then k divided by w or something like that. So let's use R for resistance. So the resistance R varies directly to its length, means that it's going to equal to k times the length of the wire. So we'll use capital L for the length. And varies inversely means that the k is divided by the area. But again, since we're multiplying the k and the L also gets divided by the a. So this gets multiplied by a basically. From the second sentence, we know that if the resistance of a the resistance of a wire is 200 ohms, so we're going to put 20 ohms. When the length is 40 and the area is 0.5, we're going to first divide these two quantities, which is 80, and k will equal to 20 divided by 80, which is a fraction is 1/4, and as a decimal is 0.25. So the resistance is equal to 0.25 multiplied by the length of the wire divided by the area of the wire. So now to the last question, or to the last part of the second sentence. What is the resistance? So we're looking for R when the wire is 140 meters long and the area is 1.75. So 0.25 times 140, that's equal to 35. And dividing that by 1.75 is gonna, again, coincidentally enough, equal to 20. And it's just pure coincidence that we get the same answer on the last two ones as what we started in the beginning, okay? Normally that doesn't happen. But this is the way we would get the new resistance, and I could continue using this formula to get the resistance at a different length of a wire with a different length and a different area. Now that concludes our examples for our notes. Thank you again for watching. If you have any questions, again, send me a message through email or through a mind. And again, I appreciate you watching, and I hope you have a great day.